Okay, so last time we talked about the distribution of the stresses, both normal and shear stresses in 3D conditions. So if you have an element in 3D, what would happen? Then it's going to be the last part of the chapter 1. Hopefully we can finish it today. That talk about a little bit about the procedure that we are using in the design. Later on when you take those design course, usually when they teach you how to design, they have the codes, the federal code or the state code that exactly walk you through the steps. But it gives you here a very overall idea of how those design codes works. So you see the last time when we did some example on material was like that. If this is the shear stress that our material can handle, then go and design the element. For example, you might go and say, okay, this is the maximum normal stress or maximum shear stress my element can handle. Then what's the remember that, for example, we have something like this. So, that's something like this. And then we had some forces applying on that. And if we know the force, and we know the properties of that material, what we did was, okay, what's the diameter here? What's the diameter here? Or what's the height here? So we use the shear stress to define those values, remember? So we can use the okay. Then you have the tau logo, and you have the sigma b logo, and then we use them to find dimensions. Remember that? Mm-hmm. So, what can go on there?
What can go wrong?
Yeah. This is the method we use to design. So, okay, we know the load, we know how much our material can bear, and then we use that, okay, so we put them together and find the dimension. What can go wrong?
I mean, there's a lot of variables that I think I'm overcomplicating things with, but just because the stresses work, one measurement works for one thing doesn't mean it's going to work for the other. And so, like, just because the shear stress is strong enough in one place, by adding that amount of material there, we might weaken it somewhere else, or like the ratio of like distribution might be thrown off. Or our math could also just be wrong, but I don't think that's the point of the question.
It's somehow correct. So let me put it in the more defined example. Assume you are asked to design a wing of airplane, and you want to make sure that wing doesn't break in the middle of the air. So what would you do? You go and say, okay, I will put it in the air. I said, I calculate the maximum force would be applied on the wing, correct? Mm-hmm. And then you, based on the material you're gonna, usually I think, I'm not sure, but I think some kind of composite or aluminum composite, something like that. Based off the material you have, you design the size of the wing. using this method. So the very first thing that can go wrong, for example, when you calculate the maximum load, how sure you are about it? How you're gonna say for sure that is the maximum, is not gonna be more than that, ever?
Yeah, that's the real world, and your blueprints are annoyingly different. And so I think that's where the problem comes in, is just because that's math world, which is perfect. And then you take it to the real world, which is not perfect, and so things are different, things can fail. You need to put safeguards in.
So I know, so that's the point. You can't tell the passenger said, hey, you know, we designed the airplane, it might work 60% of time, the other 40% of time, it might crash. So, what else can go wrong?
I mean, your measurements could just be wrong, or the materials that, like, last class you're talking about how the screw hole that we needed to round it up so that we could actually have a screw that size, because you're not going to machine a custom screw. In most cases you won't. And so maybe that messes with things, just access to the materials.
So assuming our design, usually the process is that, especially if it's a very delicate matter, the design would be rechecked many times.
Okay.
So assume, for example, as you said, the size of the, let's go there, the size of the, what was that? The pin is right.
Okay.
So what can go wrong with the pin, even if the size is right?
It can break.
It's supposed not to break. We designed it not to break.
It can fall out.
Can fall out. It's not supposed to fall out, but
No.
it can fall out. So it was 2 weeks ago. When was that? The Alaska airline.
Oh yeah.
The
door plug or whatever.
the door plug.
Plop. Yeah.
So-
then they went through and checked the
So
plates.
why do you think that happened?
I believe they said that not all the bolts were tightened all the way properly, and that was a big part of it.
Okay, so you can see it's a very real world example. They are not tight enough, but in the design, if you said you design it on the paper, said it should work properly,
Oh.
and then you have some things goes wrong with the manufacturing
Yeah.
that caused that. They were very lucky that no one hurt in that incident. Because, for example, the person who sat near the door, if he didn't or she didn't have this belt fastened, probably will be pulled out.
Luckily, that's why nobody was seated next to that spot. Luckily,
So, okay.
that's why no one was able. That's why no one got sucked up. Someone did lose their phone, and surprisingly enough, it survived the fall. But yeah.
So, again, one of them is the manufacturer. And got that part. What else can go wrong?
I mean, when you attach it to everything else, maybe it all of a sudden doesn't work with the dimensions of everything else, or
That's supposed not to happen because nowadays, previously yeah, it was, but nowadays because you reassemble these things thousands of times before putting into the manufacturing. You reassemble it in the computer, so usually, unless you're designing something that's not that important, so you just put it together very quickly.
so like 2 summers ago, I worked for a subcontractor, and the one thing that always annoyed the heck out of me was that we didn't follow the blueprints down to the dot, because our measurements either weren't exact or the scenario wasn't what fit the blueprint. And so things had to be moved over a few inches, or like I said, it was designed in math world, which is perfect, and all of a sudden when you bring it to the real world, things aren't perfect, and so that's always just, you have to adjust for the real world.
That also happens a lot, especially when you design something. For example, I've seen it a lot. You design, for example, you put a welding, very specific type of welding there, and when it goes and whoever does the welding decided that his experience is more than your knowledge, and then, for example, if you ask them to have, I don't know, 20 centimeters of the welding, said, no, I think 15 centimeters is enough. They're just crazy and they are not doing it.
Yeah.
So all these things may happen and will happen when you design. So how we are gonna prevent that? For example, assume, I don't know what's not the name of that part. The car, the wheels of the car attached to some member of the car that hold it in place. So when you design that member, you think a lot about what kind of force is gonna apply on that. So make sure that it doesn't break. And all of a sudden, the driver decided to go with another 100 miles per hour on the very big bump or something like that. So the entire thing will be brakes. So it's gonna be way overload than what you thought it's gonna be. So these things definitely will happen. So in the engineering, when we are designing, we don't think of if it fails. We are thinking, okay, when it fails, then what? So it will fail. So we want to prevent. So there are some methods to work with work that. One of them is that, okay, we'll go ahead and say, what's the maximum load that member or that whatever you designing can handle. So I go ahead and said, okay, you know, so I will go ahead and say, what's the maximum load that my member can handle? So I will go that if sigma u is gonna be the fu divided by a, and the fu is the maximum load. So, or this is the ultimate load. This is the ultimate load that member will fail after that. So I know that, for example, my member, if I put 10 tons on that, that's the maximum it can handle. It becomes 10 tons, 0.01, it will fail. Okay, so the 10 is the maximum. Even if I add the 0.01 to that, it will fail. By doing that, I will calculate the maximum shear, the maximum normal stress that member can handle. Okay, so that's the maximum. Now I can go ahead and say, you know what? I can go ahead and say, I'm calculating the factor of safety. As sigma u over sigma allowable.
What does the U stand for?
Ultimate.
Oh, okay.
So it's gonna be ultimate stress divided by allowable stress. Or sometimes they might use usually they use the stress, sometimes they might use the load. The ultimate load divided by allowable load, but usually it's like that. So how does it work?
How extra safe it is. So like these chairs probably have a factor of safety of like 2. Like on the bottom it says, oh, this chair is only rated for 300 pounds, but it can hold, like without breaking, if it's a factor of 2, it can hold up to 600 pounds then.
So basically, if I want to use that equation, which I know, which I don't know.
You probably don't know the ultimate stress.
That we can measure it. That's what we can calculate it, the ultimate stress. So we know that, so we can find out, whatever member we are using, either experimentally, if it's a new shape, or if we already know that, we can put the force on that member, see where it's gonna break. So we know that. Usually we know that for the material. So if I have a steel, I know where that steel is gonna break. If I have aluminum, usually I know where that aluminum is gonna break. So I usually know that. This part, we are gonna decide, as you said, for example, for the chair, I might have the factor of safety of 2. And then I can, if I have these 2, that gives me this one. This is the one usually we are gonna find.
I believe we talked about this in statics and dynamics in the very beginning of the class, or in one of the classes we had with you, and you mentioned how airplanes actually have a very low factor of safety.
Yeah, so why the airplane has very low factor of safety? Why it should, you think, if you want to decide, do you would put a low factor of safety for the airplane, or between this chair that you said that has a factor of safety of 2 and the airplane, which one do you think should have a higher factor of safety?
You would hope the airplane, but
why is the other way around?
Air travel has to be a lot more precise now, so it's a lot more expensive. And also they're able to control the variables a lot more.
The problem with the airplane is that if you increase that factor of safety, it's going to become so heavy that cannot fly.
Oh.
That's the problem. So you want to keep it as light as possible. So you have to find out other place. So that's a factor of safety. How you're going to decide it, again, many factors involved in defining the factor of safety. For example, if I'm designing a single home family, the factor of safety I'm using in design is different than if I'm designing the schools, and it's going to be different if I'm designing a hospital, and it's going to be different if I'm designing a nuclear plant. Okay? So you know that, for example, you want your hospital if a disaster happens, still keep running. But if you have a nuclear plant, you say, I don't want it to fail in any circumstances, because if it fails, like what happened in Japan, it's gonna be disaster. So usually those factors of safety, when you're building a single family home, says, okay, the worst case happens, the family in there. So you're not gonna make it very expensive if it's the schools, so many more students or people are there, so it should be the higher for the hospital, should be the higher than that. So this is what you're going to decide about that. That's a very simple form of dealing with all the things that we talk about it. But usually, this works for the, as I said, for example, if you're designing a chair, you might use this method. But if you're designing some things more delicate, then this is not the method that you're going to use. There is a method, and you're going to hear, depend on which path you are choosing, but usually you're going to hear a lot that they call it the LRFT. We use the LRFT to design. You'll hear that also. And stand for load and resistance factor design. So if you hear that word, as I said, usually they just say LRFT. So very quick, what we did here, actually what did we hear with that? With that factor of safety, what did we do?
We decided what the factor of safety would be?
Yeah, assume we decided, for example, the factor of safety is 2. Assume the factor of safety, if I choose the factor of safety is 2, what does it mean?
That the allowable is half of the ultimate?
Yeah, so it means that I'm decreasing the resistance of my material 50%, correct? So if my material can handle 1,000, I said, okay, let's go down to 500. That's what it means, correct? So basically you move away from the maximum resistance that your material can handle. On the other hand, remember when I talked to you about the wing of the airplane? I said, okay, you come and find the maximum load on the wing. And how can you be sure that's the maximum load? So that's another way. So we can decrease how much it can handle, or we can increase the force above what we think it's going to be. Okay? Now what, for example, in the building material, when you are usually for the structure, when they want to find a design load, so usually the design load is going to be building code. So it's going to be 1.2 of D plus 1.6 of L plus 0.5 of S. Usually in building code, that's what they are using to do work. And the G is dead load, L is live load, and S is snow. So do you know what's the dead load and live load?
Dead load would probably just be the weight of the materials itself. Live load would be anyone living that's going to go inside the building. Snow load is the weight of snow on top of the roof and whatnot. All these things would factor into the weight of a building.
So, correct. For example, if you look at this building, what we have here, The dead load is the load of material that's going to be always there. So, for example, the weight. What's going to be the live load here?
Things that aren't always here, like people.
People. What else? Desk, chair, roofing. Anything that you might bring in this room, and you might take it out of this room. If these are not going to be all live load. So anything that can be changed over the time, anything that's constant over the time, and you look at that. So you can, for example, if you look at here, we decrease the dead load 20% above what we think is going to be. We increase the live load 60% above what we are going to think is going to be. And then we decrease the snow load to the half of what we got, what we think. So, first of all, these two, why we increase the live load more than the dead load?
There's a lot more variableness to the live load. Dead load you get to design and kind of control for some aspect. Live load you can't control as much.
That's right. For example, if I design a balcony, and I design, okay, that balcony at max is going to be 10 people on that, and all of a sudden you decide to draw a party, and there are going to be way more than 10 people on that balcony. So you don't want all those people with the balcony fall off. So usually you get the live load, as I said, because the less certain, it's more uncertain, it will increase. Why the snow we drop it to the half?
That just seems like a money saving thing, because that is a little absurd in my opinion. But
The reason is that it is very unlikely that your dead load increase 20% and your live load increase 60%, and on top of that you have the very heavy snow. So these three is very likely to happen at the same time. So that's why still you want to consider the snow load, you don't want to ignore it, but you don't want to way over design, because usually that probably is never going to happen, all of that at the same time.
yeah, the Vikings old football field, they didn't have a proper, they probably did only 0.5 snow load, and their dome part of it collapsed.
Yeah. So the thing that when you go, for example, when you design the dome, usually you don't have a live load there.
Yeah.
So in that case, because you take that out, then probably you cannot put 0.5 there, because you remove that. You remove that 60% out of that. And they said, again, when you have the design, you go and to design building code, the federal code that tells you, okay, how you have to combine these. And here, I didn't, for example, include the earthquake. So you have to include the earthquake also in that combination. Again, it's very unlikely that you have the big snow and earthquake happen at the same time. Or the wind load is, again, very unlikely to have a hurricane and the earthquake happen at the same time. So here I'm decreasing the strength. Here I'm increasing the load. If I put these two together, it's gonna be LRFD. So I'm gonna do it both ways, not only one, I'm also with the other way around. So usually how we are dealing with that is gonna say that gamma D. D plus gamma L P the, this part is the, so what's this part? It's the increased load. So basically that's the increased load. This part is the reduced strength. PG is the dead load. PL is the live load. And PU is the ultimate load. And then you have gamma D and gamma L are load factor and are usually larger than phi is resistance factor and usually less than 1. And not always, but usually the load factor for the live load, the gamma L, is larger than the gamma D, usually. So that's the LRFD method. So basically it's a combination of those two methods. So we are gonna go there and say, hey, like here, we increase the design load, we increase the dead load, we increase the live load, and then like here, we are gonna decrease the ultimate strength of our material. So go both ways. Again, depend on how we want, how safe we want to be. These two are gonna be maybe larger and larger and larger, and then and this one is smaller, smaller, smaller. If we don't want it to have any safety factor, can set all of them 1.
How come we aren't using the snow load at all?
Oh, this is in general for anything. A snow load is only for the building.
Okay.
But this is the dead load, live load, and any other, basically any other load that you might have. If it's a building, you have the snow load. If it's a, for example, a skyscraper, you're gonna have the wind load, because it's gonna be important there. Or whatever you're designing, if there's any other load, it's the same thing. The idea is that LRFD, you increase the load, you decrease the strength. So that's how we are gonna deal with it. Again, when you get to the design course, So we are not gonna deal with the LRFD here. But when you get to the design course, usually the entire course is about these things, how to apply that to design whatever you're designing. So that's all the book talk about is safety. Do you have any question about it? Any part of that? Okay, let's look at the book has two examples. Let's see, can get with them. Object like this, L shape, object, that's connected at point C. Here, and there is a point. And C, there is a connection there. Point B, point meter, 0.3, that's 0.6. What else we know is that the normal stress, the ultimate is 600 megapascal. The tau ultimate is 350 megapascal. And sigma bearing ultimate is 300 megapascal. So we want to do some design here. So find the diameter of that AB part. Where's the A? Where's the A? Find the diameter of the AB, and we want to find the diameter of the pin at the C. Okay, we want to find the diameter, that's the rod. Find diameter of the AB, and there's a pin at C. We want to find the diameter of the pin at the C. Okay? So, what was the first step as always?
Figure out all the stresses.
Before that,
Reaction.
the action of the supports. So, how many supports do I have here? 2 at C and 1 at P. Because the P is also support holding. Because if the P is not there, it's gonna start to rotate. So I'm gonna have the CX and the C. So I have the CX and CY. CX, CY, there, and I have the P. So if I go for the reactions,
Then we also have B, don't we?
so that's the P, it's already there. So what should I write? The sigma of x doesn't help because I have P and the Cx. I can write it the sigma of y. I can start it with the moment. So if I write the sigma of y0, what it gives me? It 50 plus, gives me CY minus 50 minus 15 is 0, therefore the CY is 65. if I write the sigma m about point C is 0, what it gives me about point C. So I have the 50 times 0.3 minus 15 times 0.6. So, plus P times 0.6 would be 0. Therefore, the P would be, what's the P? 40 kilonewton. And then if I write the sigma of x is 0, so it gives me Cx minus P is 0, so the Cx would be 40 kilonewton as well. Right? So P is 40, C is 40, C was 65. Agree to here? So factor of safety also is 3 point, supposed to be 3. So now I want to find so the rod AB. So I want to design the rod AB, find the diameter of the rod AB. Let's see. Find rod AB diameter. So, if I want to do that, what's the first step? So I know the internal load, I know the P. So I know the internal load in that because the axial load, and it is 40,000 Newton. Now I wanted to design it that doesn't fail, and I want to make sure I have a factor of safety of 3.3.
Does it matter what material we're using? You know?
You already given the properties of the material.
Oh.
It's a steel, and these are the material for the steel. These are the properties for this.
So we want to find like the allowable using the factor safety, or the ultimate over the factor safety.
So we want to find the allowable. So this is, yeah, it's correct. This is the maximum that can handle, but we want to walk away from the maximum. How many times? 3.3 times walk away from that. So what was the factor of safety equation?
Ultimate over allowable.
Sigma ultimate divided sigma allowable. So for this case, it's gonna be, so 3.3 is equal to, how much is that?
181 point.
600 times 10 to the 6 divided by sigma allowable. So sigma allowable is how much?
I got 181.81 to the 6th, I guess.
181.1. The whole test 0.8. Can you double check?
Yeah, 0.8.
So that's the maximum. That's the maximum we want to use. That's the 600 is the maximum that 600. So the 600 is the maximum that our material can handle, but we want to have it almost 1/3. About 1/3 of that. We're gonna use about 1/3 of that, so we're gonna move way away from the how much it can handle. Now what?
We set that as our max. So we say that P is now equal to 181.8.
Getting close, but P is force. Sigma is the stress.
That equal to the force over area.
That force over area. So what I'm gonna say, that's gonna say, okay, the next step is that the sigma allowable is force over the area, which is gonna be, what was that? It's gonna P over the area of the AB. So I have 181 times, 181.8 times 10 to the 6 is equal to 40,000. 40,000 divided by area pi DAB. So DAB would be
That's 16.7 meters.
it's gonna 0.016. This should be in meter. If this is in Newton and this is in Pascal, that should come to. Unless we messed up with the unit somewhere.
I got 0.016.
0.21. Seven
Yeah.
meter. Where, so it's gonna be 60 millimeter, 0.7. Yeah, so it's gonna be 60 millimeter, correct? So that is the diameter we have. If we didn't use that safety of factors, we probably need 1/3 of that. It's a 5, 6 something. Now we want, what's the next it was asking? So we want to find the diameter of the pin at C. So I want to find the diameter of the C, and then for the C what we have is so for the C it comes like this. And the pin will go there. So if I draw out the pin, in how many points is it gonna break? 2 points, yes. It's gonna be C is gonna go. C gonna be F and F there. In fact, it's gonna look like in the 3D format. It's basically look like this. Now here. C, and you have the F, and you have the F. So how much is the C?
65 kilonewtons.
C?
See what?
C is gonna be there, so draw it there. C is gonna, I have a, you said there's a CX and the CY, and it's gonna be the C. So basically, C is CX plus CY. So, or I can say, so C is square root of 40 plus 65 would be
76.3.
how much?
76.3.
76.3 kilonewton. So that's the C. And then the same thing as before, but here we use the factor of safety instead of the sigma, we use the tau, ultimate divided by tau allowable, which would be so tau ultimate is 350, so therefore .3 is 350 times 10 to the 6 divided by tau allowable. So then the tau allowable would be get one 106.1 and you check it to see it's right.
Yeah.
106.1. That's correct. Okay. Now that I have that, so remember that you see here we put the normal, ultimate normal to the allowable normal. Here's the ultimate shear to the allowable shear. This is the same way to handle it. And then, now that we have that, we can say that tau allowable is equal to the F divided by A, which is going to be half of the C divided by area of the pin at the C. So it's going to be 10.61 times 10 to the 6 is going to be half of the C, which is going to be 76.3 times 10 to the 3 divided by 2 and divided by pi times diameter of the C diameter of the C, half of it squared, so the diameter of the C would be 0.021 meter or 21 millimeter.
What's the allowable to get that?
76.3 over 2 divided by 106.1. I divide the pi over, and I do the square root, and then multiply by 2.
So what else then? So I designed that.
Yep.
I designed that. I have to
Design that, or just check it.
check it for that to make sure if it can handle that. But not 300, 1/3 of the. But then, let's say if it says that. So it wants the thickness of this, so, and it doesn't want to have the safety factor for it. So no, it just said for the bearing you don't need to have the safety factor. just find the thickness. So, so that's the diameter of C. So it's gonna be thickness of C. So it's gonna look like this. So at the C. Then I have the force F equal to half of the CM1 there, and the thickness is T, and the diameter is the diameter of the C. I think, let me just say, I think the book did that. It says the 20.14, and they rounded off for some reason for 22. So I'm gonna just make it so if you read the book. Rounded off to 22. So 50. So for the bearing, they said it's allowable. So for the bearing, they already gave us the sigma allowable. So the sigma allowable is gonna be the force divided by area for the bearing. So bearing allowable. So it's gonna be 300 times 10 to the 6 is equal to the force, which is gonna be 76.3 times 10 to the 3 divided by 2 and divided by area. Which is gonna be, what's gonna be the area? The area is gonna be D sub C times T. So it's gonna be 300 times 10 to the 6 is equal again to 76.3 times 10 to the 3 divided by 2, and DC is 0.022 times T. And therefore the T, if we have everything right, should come out as a 5.7 0.00578 meter, or T is equal to 6 meter. You get the same number? Oh, you didn't. Again, look at here, that 3.3 is very large safety factor, because we're almost losing 2/3 of our strength. So, this is the next example. Let's see how far I can get through that. Again, we have a shape like this. At the C is also so it's hold like that, and then the dB is equal to diameter of these 3/8 of the inch, and DC is half of the inch. DA is 7/16 of the inch. Sigma U is 60. Tau U is 40. And the factor of safety is 3. So the first is going to be the, again, just the reactions. First step, so I'm going to just redraw that again. So if I have that element, there, I'm going to have D here, this one is 0. I don't have any horizontal force because there's no horizontal force acting on that. And then I have the force at C. I have the force at making the force at D. And then, so look at there, I have three unknowns. So if I write the sigma m about point D 0, but I'm going to get that. That's is 6 inch. That's 8. So what I'm going to get is that f at b times 14 minus f at c times 8 would be 0. So if I simplify that, it gives me the fc is going to be 1.75 of the f at d. If I write the sigma m at b0, so it's going to ft times 14 plus fc times 6 would be 0, and it tells me that fc would be 2.33 fd. So I have these two equations, so I know that these two equations. So basically this problem, what it's asking is that, you see, we have all the dimensions. It says, what's the maximum FC before this breaks? So what's the maximum force I can apply on that part with this factor of safety of 3? That's what it's asking for. So that's what's the maximum FC. So they're using, the first thing that they're going to use is the rod AB. So they say, if the rod AB is going to be the one that failed first, what would be the maximum FC? Okay. Rod AB. So assuming the rod AB is the one that's going to fail first. So again, we have the ultimate so factor of safety is the sigma u divided by sigma allowable. So it's the 3.3 is equal to 60 divided by sigma allowable. So the sigma allowable would be 20. Now that we have the sigma allowable 20, I know that cannot be much more that I can say, okay, the sigma allowable is going to be the maximum of FB divided by area of the AB. So the 20 is gonna be the FB max divided by area of AB, which is gonna be pi times the AB is 7.60. 716 divided by 2 is 716 divided by 2 to the power of 2. The area of the diameter of the AB we are given here. So then the F max, FB maximum would be 3.01 kips. Kilopons. And if this is the maximum for the FB, how much will be the maximum for the C? Look at here, I have these two equations. One of them should be big.
I think the top one's.
Yeah, the top one's supposed to be, it's the B.
So now I know, so I assume this is equation 1, this is equation 2. So if I use the equation 1, then how much would be the maximum? So if C max would be 1.75 of FB max. So if C max is 1.75 times 3.01 would be 5.27 cubes, if I have it right. So look at, let me walk you through what happened here. I would say that if AB would be break first. Okay, this is what I have. I don't know either of these three. I want to know what's the maximum of that. So if I want to know the maximum of that, it's gonna break either here or it's gonna break either there. Okay? So if it's breaking here, so I said, okay, let's see it's the AB, it's breaking the AB. And then I want the safety factor of 3.3. So I find the allowable safety factor. And if it's my allowable stress and I know the area, I would say how much force I can put on the B before the AB breaks. So I will find the maximum force I can put on the AB before the AB breaks. And when I find how much force I can put on the AB before it breaks, then I can calculate the FC factor. Did you get the logic of what happened? So next, that I'm gonna check to see if it, assume the next one is gonna break, assume that it's gonna break at the point B. So the pin at the B, assume breaks next. And B. So you can see if it If it breaks at pin B, what would be the force we need to apply? What's the maximum, or in other words, what's the maximum force that makes it to break at pin B? So that's the maximum force that breaks the AB, the member of AB. Now, so what's the maximum force that makes it to break at the pin B? And the pin B is book drawing. So the pin B looks like this. There, and then we have the, call it the F1 there. And in this one, again, now we want to look at the, we want to find the factor of safety, but for the shear stress, it's going to be tau ultimate divided by tau allowable. So, therefore, the 3.3 would be tau ultimate is 40 divided by tau allowable. Therefore, the tau allowable would be, how much it would be? 13.3. So that's the maximum tau I am allowed to use. Now I'm gonna use that equation. The tau allowable is the force divided by area, which is gonna be half of the FB divided by area of that B. So look at here, I want it to break. So that's gonna be my maximum, the FB here is gonna be my max. So how much it can tolerate? 3.30, 13.3. What's that? I want to max it, so it's the FB max divided by 2. How much is the area that I have at the B? Is a pi 3/8 divided by 2 to the power of 2. So FB max would be 2.95 kips. Now I have again the FB max, so I can use again the equation 1. And it says that FC max would be 1.75 times FB max. So FC max would be 1.75 times 2.95, which would be 515. So very quickly before I move to the next one. So what does it tells me that FC max is 5.2.7?
That's the non.
It means that if the FC, if the amount of FC becomes 5.27, it's gonna break at AB somewhere here, correct? If it becomes 5.15, it's gonna break at the B. So what does it mean? if it is 5.27, it means that it's already broken at
5.15.
B. So if I put force here and increase it, the B will break before the AB breaks. Correct? So between these two, which one can I use? The smaller one. You got that? So now, what else left here is the pin at the D and the pin at the C. You have to check those two as well. So pin at which one is it first? It's first D. So pin D, if you look at it, pin D is in any way is similar to pin B. Okay, so they are very similar to each other. So pin D is similar to pin B. So because it's similar, so if it's similar, so I know that then the tau allowable, therefore the tau allowable is 13.3. But they are the same. And if I write it, it's going to give me the very same magnitude. So if I write it tau allowable, it's going to be the F divided by area, so it's going to be the F at D divided by 2 at the area of the D. And exactly the same, so it's going to 13.3 is equal to FD max divided by 2, and the area is going to be exactly the same, so 5 3/8 of the inch divided by 2 squared, so FD max would be the same as here, 2.95 cubes. And then, so up to here is the same. Now, look at here, I have to use the equation 2 instead of the equation 1. So now the difference is here. So the equation 2 tells me if C max is 2.33 F D max. So if C max would be 2.33 times 2.95. This is gonna be 6.77 kips. So again, if you look at it, it will all still it will break. If it's 6.77, it already those two are broken. So we never get to 6.33. And then the last one is the pin C. So the last one that left is the pin C. Again, we know that the tau allowable is 13.3, so we don't need to calculate that again. And then we know that the sigma allowable is going to be F divided by area, and in this case it's going to be is going to be FC max divided by 2, and then the area here for the C is half an inch. So it's going to be half an inch divided by 2 to the power of 2, so FC max would be so if you look at here, the number I have are
Hey,
Wait,
sorry, I have a class.
oh, I'm sorry.
just a little bit longer.
So the number we have is 527, 515, 6 sevens, and 524. So which one would be the maximum we can use? So the maximum force I can put on the maximum that I can put on the C is the minimum that I have here. So it means that if I go on any other of the values, it already breaks. So basically you have to check it, check each member one by one to see that